Hey, what's going on, guys? KIM-1 here. I'd like to welcome you all to my new show, like programming in 6502. Not really live coding. Actually, I have already prepared a program that we're supposed to be writing in this video. And just a few words in regards to the environment I'm using to make it a bit more clear. So I'm using the keyboard to enter the code and this VGA monitor as an output. My KIM-1 emulator, so I'm running the KIM-1, is running on this ESP32, so I hope this makes sense. And I have some software being installed here. So for instance, I have at 9548, I have the supermon 64 by Jim Butterfield, which allows us to do a whole lot of things. And what we're interested now is assembling. So I can assemble line by line. But the problem is that let's say I want to assemble like 400s, for instance. I want to say like LDA and like 10, and then like LDX and whatever. Then yes, it works. I just did assemble this kind of two lines, but what if I want to move it somewhere, put something in between? So literally the problem with this assembler is that it doesn't allow editing. And I was thinking, how can I actually change the super monitor itself in order to, instead of doing this line by line, so I could have taken the source code, the assembly source code from somewhere else, from the RAM, and feed that source code to this assembler, so that I could edit somewhere, and then whatever is already kind of available in the file, like all the instructions that are about to be executed. So those instructions, just to feed them one by one to the assembler and to get them assembled, but not by typing them directly, like not on the fly, but from the file. So something like the modern assemblers work, basically. So how you might be wondering, I'm going to be hacking around this. So let's just reload things. And this is how. So if we have a look at 2000s, here I have Tiny Basic by Tom Pittman. And yes, obviously you can do things like printing hello world, but it's not really that useful, right? So this Tiny Basic is not really that powerful in terms of like Microsoft Basic, for instance, or something, but it has an absolutely incredible feature, which is the code editor. So you don't necessarily need to type basic commands here in order to store that. So for instance, you could have write like some custom commands here, like say 10, for instance, and then remove, and then A 0500, and for instance CLD, clear the decimal flag, and then I could have say like LDA and 12, and then like 30 like LDX and 13, and then if I list, then I have some bytes, some ASCII bytes being stored in my random access memory. Obviously, if I try to run this, it would give an error because this is not basic. This is gibberish from the basic perspective. But if I somehow manage to fit this lines one by one into the assembler itself, in that case, it will be possible to actually assemble the whole file that we have here in BASIC. And the benefit of doing so, as opposed to doing this on the fly in the supermon itself, is that we can alter the lines, we can add the lines, remove the lines, like put lines in between. Say if I say like 25, we would put the line in between. So it's not about how we can edit the source code in BASIC. You probably know this, but it's about how to actually take these instructions and feed them directly to the assembler. So now let's reboot, and I want to demonstrate another little thing here. So there is a nice address. Let me just quickly check up my notes. The address is 9596, and 9596, and here we have this is so-called ST1 label of the super monitor. So it goes within the main loop, and the idea is that if I run the code starting from 9596, what it's supposed to be doing here, it's supposed to be decoding the instruction, whatever we have, and then it would try to execute that instruction. So just to split the process of this assembling a little bit, I can show you the following tricks. Let's say we go to 9548 to invoke the assembler, and A, and I say, for instance, 0500 and CLD. And now I don't press enter, I just press escape and I trigger the non-maskable interrupt instead. And if I go to 0200, we have 41, which is the ASCII character of A, this one. Then we have 20, which is the ASCII character of space. 30 is ASCII character of 0, 35 is 5, 0, 0, then space, and then CLD. So these are the ASCII characters for CLD, followed by 0. If I do this casually in a loop, click enter, invoke the carriage return, the carriage return will be automatically replaced by the 0, and bear this in mind for future because we're going to be using this in our code. But for now, what I can do, if I have this input in the memory, if I now go to 9596 and say Shift-G, then you see like it auto-completes, and actually I find myself in the address of A2. Actually, I find myself in the main loop, right? I find myself in the main loop. So I just escape from here, and if I just now inspect this 500, then suddenly you see like the D8 appears here, which is the code for CLD, clear the right directional flag. So it did exactly what I asked it to do. So at the address of 500, it assembled the CLD to D8, which is exactly the case. But there is a problem. I don't really want to drop back to the main loop after this occurs. So there is another hack for achieving that goal. So let's reload this one more time. And now this address A0 to F, and here. So for instance, yeah, actually, this jump after the line is assembled and after the next address has been calculated and just put there, so that you don't need to type the address every time when you're assembling. So after all that happened, it just drops back to the main loop. So in order to avoid this, I can just put 00 here to cause the break. So for instance, A20F, A20F, and I put 0 there. And now again, now let's go even more hardcore. So we'll now encode the instruction by hand. So here I have the instruction to encode LDA and some value 12. Yeah, LDA 12. So for instance, if I now go to 0200, okay, nothing there so far. So I say 41, which stands for ASCII character A, then space 20, then 33, which is 3, 30, and then 30. Okay, so 300s, then space, and then LDA, so 4C for L, 44 for D, 41 for A, then 23 hash symbol, 24 $sign, and then 31, 32, which is 1 and 2 respectively. And then we go with the 0. If I now go to 9596 and run the code, you see like I'm no longer in the main loop. I just drop back to the key monitor. Meanwhile, if I go to 500s, oh, it's not because 500, it's now in the 300s, I'm sorry. If I go to 300s, we have this A912, which stands for load accumulator instant like media data addressing mode with a 12. So just assembled properly what I've typed by hand from this sheet of paper. So now our goal is simply to automate the process. So let's try to imagine the entire picture. And to make it better, to make it easier, I would now walk through the source code. So let's just reset this. We don't need this for now. I will now walk through the source code of the program I've written. And by the way, the reason why to do this, like eventually, is because currently the only way to develop something on this computer is just first write the program on a piece of paper and then just put it in. Even it's much better, easier with assembler. You don't need to do the hand assembling, but still, it's not intended to develop just right on the computer. So you're literally developing on a piece of paper, on this sheet of paper, and it's not always that handy. So with the power of the basics line editor that can code the lines, you can like manage the assembly lines however you want, and then you feed them to the assembler. You no longer would need to write the code on the piece of paper, and that's the enhancement that I'm currently working on. So the first thing that we've done so far, so at the address of A030 and 31, it's where the program is going to be jumping after the assembly was completed and was okay. So I'm jumping to the address, so LDA2F, and store the least significant byte, 04, and store the most significant byte. So this address 042F is the place where I want to drop back after the assembly, the assembling of a single line has been completed. So I'm dropping back here, and literally here I would be going to the next instruction. And if there is a next instruction, so if there is no 0. So branch not equals, it's not 0. Branch not equals might be read as branch not 0. So if there is some instruction still, not a 0 terminating character, then we just drop back to the main loop and fetch another instruction and work with that instruction. So let's walk through the source code. Oh, sorry, just pushing this. It's not on the cards. Okay. So first we initialize the redirecting jump that is going to be bringing us here after a single line of code has been executed. Then this 2 knobs is just a placeholder, so I'm going to be storing the values of the X and Y registers. So Y register goes here, X register goes here. So I'm going to be storing them before making this jump, because when I'm assembling, the X and Y registers would just get some whatever values, we would get those values that we have here. So we need to make sure that we can store them and then restore them back. So these 2 bytes are just for that purpose. It's not the best ever place, probably better doing this on the 0 page, but anyways, this matter works like so as well. Then we initialize in the Y and X. So Y is indexed to the 200th address, so it's literally going to be pointing to the next byte where we want to copy paste the instruction from the editor to the execution part. So it executes, so the assembler actually reads the next instruction from 200 hexadecimal. It reads one instruction at a time. So LDY starts from 0, LDX starts from 06, because there in basic, you remember we had like 10 space RAM space and then A. And that and this 6 is address of that exact A, because first we need to specify the origin. We need to do this only once. Once we've specified the origin, the address would be updated for us automatically by the assembler itself. So X actually points to the editor's scope where the basic program is stored. Well, it's not a basic program, it's an assembly program, obviously, but it's stored using the basic interpreter. So X register points to where the basic program goes. Y register points to 200s. Well, not to 200s exactly, but it just points to where we should go, where we should kind of paste this instruction from like 300 space where the basic stores the code to 200 space where we want to fit a single instruction. Okay, that's clear. Then we load whatever we have at 300. So 300 is where the basic program is stored, indexed by X, and it's going to be incremented to walk like character by character. And we store this to where the Y is, but already at 200. So literally, this is copying the memory. These 2 lines are written like basic code, and here, this line is reading the assembly code from the basic editor, and this line actually stores it to later feed to the assembler. So now we increment both X and Y indices to go like, so Y would now point to the next character, X also the next character. Then we need to make sure that if we do encounter 0D, which is the carriage return, this means that that's the end of the instruction. In this case, so if this occurs, then this logic goes. If not, we just continue to, here. So adding like copying character by character until we reach the end of the line. So once we've reached the end of the line here, once we reach the end of the line, then we need to do the following. So loading 0 to accumulator, decrementing Y register by 1, and putting there whatever we have in the accumulator, which is 0. So literally we're replacing the carriage return with 0, just like the original program does, because that's the only way how we can understand things. And then loading 7 to Y, because the next time assembler would be called, it would already put on its own. It would put the it will put the next address to assemble into this 200s scope. So once we do this once, it then would be like the next address, and then it only waits for the next instruction. So hence Y points from the, so only first time it goes like 0, and then it goes to 7 because the address has already been calculated. Also, we skip 2 characters, 2 bytes in the source because they're just like basic separators, which we don't need. And after, we store in the value of Y register and X register, which points to exact places in like where it should resume while the next instruction occurs. And then we assemble the instruction. So this jump actually assembles the instruction. Then we restore back our values. And then finally, all we need to do, we need to make sure that if the next character in the source, we load in the next character in the source. And if it's not 0, then we just go in back and trying to find the next instruction to execute. And that's pretty much all about it. So now let's code this in and see how this works. Okay, so I just reboot my computer one more time, and I'm going to 9548 Shift G, and I'm trying to assemble at 0400. So the program that I've just described is going to be living at 400 hexadecimal because I just decided that that would be the proper place. So let's go LDA and 2F STA at A030. Okay, LDA 04 STA A031. So again, here we just fake the jump ready ragged out. Instead of going to the main loop of the assembler of the supermonitor, would be coming to the specific address of 0204, which is here, which is where we should drop back after the jump occurs. So regularly it would go to the main loop of the supermonitor, but we want to go here. So hence this address. We're loading this address 04 Okay, then we have a couple of no operations. These are going to be the placeholders for X and Y register storage variables. However, if I do them zeros, it would just break and the program was not going to continue, so that's not on the cards. So now I say LDY, so initializing the Y register. Okay, and I just made a mistake. Okay, it's not good. Okay, let's go to 400s again. Anyways, we have the addresses. So starting at 040C. So yeah, it's right over in here, 040C. Hope you see this. This one. So nope. A 040C LDY 00. Okay. Now LDX 06, because that's the offset for the very first character in the source code from the basic editor. Okay. Then the main part, copying the bytes character by character. So LDA, I'm loading at 300s, index by X, and I'm storing this at 200s, index by Y. Then I need to increment both X and Y registers. Okay. Then comparing whatever we have in the emulator with 0D, which is the carriage return. And in case if it's not the case, if it's not the carriage return, we branch not equals to 410. So branch not equals to 410. I'll later show you this address. It should be here 410. Okay, when I disassemble this would get more clear. Where exactly do we jump? Then LDA 00. So accumulator is now equals to 0. Now decrement in Y register by 1. So the Y register again, like it points to where the assembler is going to be looking for. So now we're going to be replacing the carriage return from the source code with a 0 to make sure that assembler understands things properly. So I want to say STA 0200 and Y. Okay. And now the new value for Y register is 07 because we need to make sure that we shift enough to make sure that the updated address, like with the next instruction, is already there. So we need to make sure not to overwrite that. So we need to shift a little bit. Okay. Next, we skip 2 characters. What have I done? Okay. Again, disassemble. Okay, so started at LDA 07, so 0424, assemble 0424, yes. Now increment X register twice. So go into the next character in the source code, and I want you to store the values of Y and X register to make sure that the next instruction they don't mess up. So STY, so Y register is to be stored at 040A, and STX is to be stored at 040B. Okay, now the most important instruction to actually assemble what we currently have at the 200s line. So here I want to say jump 9596. Okay, and then now the X and Y registers were malformed, so we need to restore them back. So I can say LDY and 040A. Okay, and then LDX and 040B. So we just restore those values. And well, we can actually stop here because so far it would just it would execute the single instruction. But since I'm afraid to mess up things a little bit, so I will probably just complete the code to show this all at once, because otherwise, yeah, I would need to retype things. Even though I have the option to store the entire emulated RAM to SPI FFS, but anyways, okay, so let's complete this. So now we are loading whatever we have in the source code, so at 300s indexed by the X. And in case if we encounter a 0 there, that means that no more instructions are available. In this case, we can say branch not equals. So if it's not 0, then there is an instruction. So only there is an instruction. We branch to 410. And if I typed everything properly, now in theory it should be working. So let's inspect from 400s to 42C. It would be almost all of the code. So just to make sure that everything goes well. So loading to F in the accumulator, storing the least significant byte at the most significant byte at the redirect address. Okay, 2 knobs. So Y is 0, X is 6. So loading the character from the source, storing this to fit the assembler, updating, like incrementing both registers, both indices, comparing what we have in the A register after this instruction with the D. If it's not, then we just go back to 410, which is here. So this is correct. We don't need to reinitialize every time, so only here, so it goes here, right? But then let's say we encounter the end of the line, so then this doesn't fire, then we go here, so going as 0 goes to the A register, decrementing Y, and replacing the carriage return with the 0. Then the new value for the Y register is 7 to make sure that the address that has been stored is not being overwritten. Then go to the next line in the basic editor source code, and then we want to store both X and Y registers, assemble the line, and finally after assembling the line, we restore the X and Y registers, and we were looking whether any instructions, any source code still remains in the basic editor. So if this results in 0, then we're not jumping back, then we just break here. Otherwise, if there is some ASCII character, if it's not exactly ASCII, not obviously ASCII, but whatever, a non-zero character, then we go back to 0410, which is 2 lines above. You understand this. Okay, so we got a hopefully working code now, and now all we need to do is to go to the basic G and list. So we don't have anything there so far. So now we're gonna be assembling. Now we're gonna be writing our assembly source code. So let's, for instance, say 10. The line numbers doesn't matter in this case at all. So you can have whatever line numbers, they would be skipped by this program anyways. So RAM is needed because otherwise it just malforms the line numbers for basic and just doesn't work nicely and edit any longer after. So here, so this should be 0, 1, 2, 3, 4, 5, and 6 is spaced. So starting from next one, that's why we initialized X with 6 initially. Okay, so here, assemble. So this is the A that I would have otherwise write in the assembler itself. And I want to be assembling this to 500s. Okay, and for instance, I say CLD, which stands for clear decimal flag. So far, so good. Now I go in here and I want to say LDA 12 and 30, LDX 13, for instance, and 40, LDY, and 14. So we have 1, 2, 3, 4 instructions to execute. So let's list our source file. So we got it there. So far, so good. Now we drop back, and now I hold my breath. I tried this; it kind of works, but I just couldn't make some typos. So, anyways, let's have a look at 500. So nothing there so far. But now if we go to 400s, where our program actually is that we've just written, so go into 400s and G to execute. And I already know that it works perfectly well because every dot it prints means that the line has been assembled successfully. Otherwise, it would just print the question mark and it would stuck somewhere in the supermon loop. So from this, we know that everything has been assembled properly. Now, just to make sure that this is indeed the case, I can go to 500s, and we have D8, which is CLD, A912, A213, A014, which is exactly what I'm reading. So LDA12, LDX 13 and LDY 14. Just to make sure that this is the case, I can go to 9548 and G, and now disassemble at 500s, and you see that we have exactly what we've written in our source code, but now it's actually being assembled to the 6502 bytes. That can be understood by the processor. Okay, guys, this is it from my side. I hope you've enjoyed this 6502 coding show. Let me know in the commentaries if you like this format and if you want to see more. This is it from my side. Thanks for watching. Until next time, and take care.